Hybridization is a major player in the approach to bonding. There are two ways that the orbitals can overlap to form bonds. So this is kind of you have one which is called head-to-head overlap. A sigma bond is head-to-head overlap and is what always happens first. Okay, whenever you have a carbon bond to another molecule, let's say it's oxygen, a sigma bond or a head-on overlap always happens first. So I'm drawing the p orbital. See how they overlap? That right there is an example of a sigma bond because it's the head-to-head overlap of two particular bonds. This right here is what determines the molecular geometry and is the stronger of the bonds. So you have this cylindrical symmetry. So you can take it and you can kind of twist it, turn it, but at the same time it's stuck together as one kind of free to rotate bond. So the fact that a sigma bond is free to rotate and is the strongest of the bonds because it has this head-on-head overlap. Now another type, these are single bonds, and these sigma bonds are very energetically favorable. They like the overlap. So sigma bonds are the single bonds and require the most amount of energy to break. To break a sigma bond requires a great deal of energy. Now it depends on the atoms and all that kind of stuff, but it requires more energy. There's a second type of bond that's called a pi bond. And pi bonds are characterized by a side-to-side overlap. So once again, I have my carbon and I've got my oxygen and they overlap already in this orbital. But then I want to form a double bond between them. Realize that you have a p orbital that goes this way and a p orbital that goes this way. Now I didn't draw it, but part of these two things are going to overlap. When part of those two side-to-side characteristics overlap, that's what we call a pi bond. Now, as you can imagine, this is not nearly as much overlap as you expected with a sigma bond. Okay, there's a lot less overlap. Because there's less overlap, it's easier to break this bond, and this bond is what we get when we get multiple bonds. So pi bonds are not as energetically favorable. They're the second or the third bond. So when I see here nitrogen, one of these bonds is sigma. The other two are pi from the side-to-side overlap. Okay, now pi bonds require a lot less energy to break because there's not as much overlap between them. But they still do require some energy. So when you're trying to break this thing, if you break one bond, you're breaking the pi bond first. Then you're breaking the second pi bond, and then you're breaking the sigma bond. Now, whenever you have multiple bonds in hybridization, when you have sp3, and this is only, we're talking about carbon here. Carbon is all we're talking about. sp3 indicates all single bonds. The reason why is you have carbon, 1, 2, 3, 4. So that's indicating the presence of 4 single bonds. When you have sp2 hybridization, that's indicating the presence of a single double bond. Now, when you have sp3, that indicates the presence of a triple bond. So based on the molecular geometry, you can predict the hybridization, or given the hybridization, you can predict the geometry. Okay, here's an example question. It says, rank the bonds from easiest to most difficult to break. So if we're looking at this, we're going to start with what we call the central atoms. Okay, this is going to be one of the central atoms. This is a central atom. This is a central atom, and this is a central atom. Okay, so if we're looking at this based purely on what we know, we're going to predict, first of all, that the toughest one to break is going to be this one. The reason why is the first pi bond is easy. The second pi bond is easy. But the third, the sigma bond, is going to be tough. Because of that, I've got 3 bonds that I've got to break in order to break this. So the triple bond is always going to require more energy than a single bond because it is a single bond, but then 2 other bonds. And even though this is less, it's still there. This bond is going to be second because I've got to break a pi bond, and then I have to break a sigma bond. So now we need to look at the rest of them in terms of how easy or difficult are the bonds going to be to break. You have a carbon attached to 3 hydrogens, and another carbon, and then you have a carbon that's attached to 2 hydrogens and then double bonded to another carbon. So because of this, it's beyond the scope of this class to predict which one of these hydrogen bonds would be easiest to break from here. Now you could probably predict based on what you know of electron geometry, but for now we're going to say that breaking this carbon-hydrogen bond is going to be the same as this one, which is going to be the same as this one, which is going to be the same as this one, which is going to be the same as this one. Resonance structures. We've already briefly touched on resonance structures, but molecules can have multiple arrangements of bonds and electrons. This is especially true with double bonds. Whenever you do this, there's a lot of ways that you can manipulate the structure by moving a pair of electrons to form a double bond, or taking the electrons away from a double bond and adding them to an element. Now, either one of these particular resonance structures are equivalent. We have no way of knowing which one it actually is, especially when you consider there's a negative charge here, which is very close to a negative charge there. Okay, but there are some resonance structures that are more correct than others. So you need to be willing to look at the formal charge to make sure the formal charges balance out. For example, if I had some sort of structure in which I had this was positive and this was negative, and then I had a negative, I would know that that would be wrong. There's got to be some way to cancel out that positive and negative and just leave the one negative charge. Resonance structures. All of these structures are equivalent, no way of saying which is accurate. So a lot of times what you do is you create what's called a hybrid resonance structure. So I said I have a double bond, I have a double bond, and I have a double bond. So because of that, what I can think of is like there's a third of a double bond there, a third of a double bond here, and a third of a double bond there. Well, if I think of it in those sorts of terms, I have a total negative charge of 2. And I have 3 atoms on which to split it. So you can think of these 3 equivalent structures. Okay, these 3 equivalent structures, you have a hybrid structure that you see right here. This bottom middle element would be considered to be a hybrid structure because it's a combination of all 3. Does that mean that this is really what occurs? And the answer is no. But since these 3 structures are equivalent, and I don't know which one it is, sometimes you will see chemists draw it like this as a temporary sort of explanation of the resonance structures. Resonance structures. Resonance structures are delocalized versions of all resonance structures. The most famous one that you'll see is benzene. Whenever you see benzene, benzene represents a ring structure. Now each point on the ring represents a carbon. So benzene is C6H6. And if you were to look at this, you see the connectivity of it is such that when you have this structure right here, this carbon right here, actually let me draw it out a little bit better so you can see it. So it's going to be carbon, double carbon, 2 carbon. That's 1, 2, 3, and then we draw carbon. So this is what you see as far as the ring structure is concerned. So each one of these carbons can hold 2 additional electrons. But because of benzene, it has a double bond here and there. So each carbon can only hold a single hydrogen. So you see 1 hydrogen on each. Now there's no way of telling whether the double bond is actually here, as you see it drawn, or here, or here, or here. But if it's there, I'd have to cancel out the 1 double bond on the other side. So you have no way of knowing which one of these resonance structures is correct. So benzene, more than any other molecule, because it's so prevalent in organic chemistry, is actually drawn with a circle in the middle. The circle indicates the 2 resonance structures, and what happens is these pi electrons become what's called delocalized. So where these 2 pi orbitals are overlapping, the one next to it is also kind of overlapping. Kind of messed up my structure there. Okay, they all kind of overlap together. So what you have is you have a delocalized version in which all the electrons are kind of shared between the molecules. Now that references only the pi electrons, not the sigma electrons. So this is where we come to molecular orbital theory. And molecular orbital theory is an extension of hybridization based on the wave nature of the electrons. So whenever we look at the wave nature of electrons, we produce what's called a bonding orbital and an anti-bonding orbital. Now a bonding orbital is one that's lower in energy, and an anti-bonding orbital is one that's higher in energy. So bonding orbitals, whenever we look at a bonding orbital, the reason why it's lower in energy is the fact that the electrons can interfere in a constructive manner. So we treat one electron as a wave and the other electron as a wave. When they overlap at the same point at the same time, we have what's called constructive interference. Whenever you have constructive interference, peak overlaps with peak, you get a bigger wave and you get a more stable bond because the electrons are interfering constructively. Now, whenever you have an anti-bonding orbital, that's when the electrons overlap peak to trough, and when you add them up, you get a straight line. Because of that, that actually raises the amount of energy necessary to put electrons together, and you get promoted to where you have an anti-bonding orbital. Now, generally, we think of the s orbital as being kind of right here. There's the 1s orbital. The bonding orbital is lower in energy, so that's energetically favorable. The anti-bonding is above this, so this is considered to be an anti-bonding. It actually raises the energy. So bonding orbitals will actually promote bonds between the two atoms. Anti-bonding orbitals actually detract from the bonding capability. So if you have just the bonding orbital filled, yeah, you have a bond. But if you have the anti-bonding orbital filled, you have no bond. So here we talk about energy and bonding again. So remember, the energy of the bonding orbital is below the atomic, and the energy of the antibonding is above the atomic. So there's no net gain to an atom. So like say I'm a hydrogen atom, and I put one electron here and then one electron here. Well, I might as well have kept my electrons to themselves if I had two of them. Okay, helium's a better example. I would put one electron in the bonding and one in the antibonding, and then now there's no gain. I might as well just keep my electron. So if you have something where the bonding and the antibonding are filled, that tends to not form a bond. And then what we do is we calculate what's called the bond order. The bond order determines if a bond will form and determines how many bonds will form. So the formula that you have is 1/2 of the bonding electrons minus the antibonding electrons. And when you multiply it by the half that we originally said, that will actually tell you the number of bonds that form between two elements. So an example of that is if you have hydrogen, you have molecular orbital theory. It says 2 electrons go into a bonding molecular orbital. So I've got 2 electrons from 2 different hydrogens. Both electrons go to the lowest energy state, okay, because we always fill from bottom to top. And because of that, there are no bonds in the antibonding. So the antibonding is empty. Okay, because it's empty, there tends to be a bond that forms between hydrogen and hydrogen. So we get H2. The bond order is 1 because when I do 1/2 of the 2 electrons in the bonding orbital minus the 0 in the antibonding, that gives me 1, which indicates there's one bond between these two hydrogens. Now when I look at helium, I've got 2 electrons in each. They first both contribute 1 electron to the bonding orbital and 1 electron to the antibonding orbital. Because of that, there is no net gain in in energy. So because of that, the atoms tend to not form bonds, and that's why you don't see this in nature. This does not occur. Okay, so that's why noble gases tend to not form bonds with other molecules, because they don't gain anything out of it energetically speaking. Remember, nature wants to lower the energy as much as possible, and that doesn't happen here. So since that doesn't happen, this doesn't actually work. And if I were to calculate the bond order, I would say 1/2. I've got 2 electrons in the bonding orbital, minus I've got 2 electrons in the antibonding. 1/2 of 0 is 0, so there are 0 bonds that form between these particular substances.